And then I'm going to take the attendance check.
Oh, you're not recorded. Oh, you already recorded?
I'm recording, yeah, right now. I haven't recorded yet. Yeah, I'm recording now.
Okay. He doesn't even move anymore.
Good enough.
Yeah, it's a pattern.
Increases as the semester increases.
I can kind of say who is sitting where. Okay.
Okay, so next class, everyone moves seats.
Yeah.
I know, right?
Yeah, this is actually very strict on EE majors taking summer class. I'm teaching thermodynamics for EE majors. Everybody sits in the same spot in every single class. They never move. So I almost thinking of stopping taking record because it's like the same thing every class. EE majors are very, I don't know.
Is there any funny stories you can tell us from their presentation on Tuesday?
Presentation on Tuesday.
Was there anything funny?
Was there anything funny? What presentation you talking about?
I don't know, something with 200 degrees Celsius water?
Yeah. Well, there is an ANSYS simulation, and then they said the temperature of water is 190 degrees C. Then I said it's not the liquid anymore. It is superheated vapor. So phase change must happen. So anyway, something was wrong on the heat transfer simulation.
Did it also like 1,000 degrees or something?
No, it's not that strange. I mean, that's so obvious. Everybody laugh at it. We got a water temperature here 1,000 degrees. People laugh at it. It's not even realistic. I mean, it's not the physical.
Wait,
It's impossible.
Water boil at a higher temperature when there's more pressure, or?
Water boils less temperature if you have higher pressure.
Okay,
So not the other way around.
Yeah. No, because water boils faster at sea level than it does up here.
That's right. So yeah, here water boils in much lower temperature.
No, it boils at a lower temperature than the.
Yeah. So should higher pressure should be a
Yeah, that's opposite. Sorry,
Yeah.
I said wrong thing. Lower pressure, boiling temperature goes down. So right here we have mile high. Your water starts boiling much lower than 100 degrees C. So you cannot cook noodles for your lunch.
Robin here?
Okay, so yeah, so at 5,000 feet, it says it boils at 203 degrees Fahrenheit as
Yeah.
opposed to 212 at sea level.
So it's much lower temperature. Yeah.
Fahrenheit, what's that?
Oh, sorry, I forgot the C stands for can't land on the moon and the F stands for Fortnite.
Yeah, that's recorded in the lecture now. That is going to be rewatchable.
Oh my God.
It's amazing you still have a time to do games. How do you squeeze out that kind of thing?
You make time.
Okay.
It's a sleeper games. You can't do that.
Yeah. Okay. My son used to play that, but
Oh.
he can't do it now.
I still don't know how it's relevant.
Yeah. Okay. So today's lecture is.
Me too.
I can tell you the motivation is rock bottom. You don't want to talk about airplane.
All the 10-year-olds. This is not the future.
You show up in class and you don't want to talk about airplane. Okay.
We just spent an hour talking about it, so.
Yeah, because that academic break is really ruining. It's just destroying the week. Your motivation is like.
Why are you put in the middle of the week? Make it on a Friday.
Right? Give us a
3-day weekend.
They don't give us long weekends, they put us back in the middle.
That's exactly what they're trying to avoid. If
So
you
they're trying to
give.
kill our motivation for the entire week, but not.
Yeah, that's
No, because long weekends, people will try to travel.
No, you
Yeah.
see, and you're an engineer. What do you-
True.
Yeah.
But there are also business majors that go to this school that still have time.
Okay.
No, they either play video games or they go to sleep.
So basically, you are saying that we are engineering majors, so we need a Friday instead of Wednesday.
Yeah.
Yeah.
We're not biology major.
If that's the strong voice of students, I'll take it up to next college meeting.
Yeah, you should.
Yes.
Okay, I'll tell Dr. Madra, hey, this is what the students are saying, they're upset.
Actually, you should just tell me we need a spring break.
An entire week instead of just like 3 days broken up over
You
several
mean
weeks.
two?
Yeah.
It's actually three.
There's one more coming.
Okay.
That was fine. That's it.
Yeah. Well,
Wait, there's another one?
no,
No.
Oh, there's not one more?
No,
Oh,
that's
well,
Okay.
3 more weeks, you're gone.
Yeah, I was gonna say another one? Oh, yeah?
then Malay lied to me.
Okay.
It's not recorded.
Alright. So, okay, let's begin, okay?
Oh my goodness.
Yeah,
Maybe you should record it one.
yeah, okay.
Outtakes from AE317.
He needs a little, he needs that little like, director thing. He needs to put it on the camera.
Director's cut.
Yeah. Take two.
Yeah, so we are going to pick up PS diagram, okay? And then the other diagram is maneuverability or energy maneuverability diagram. So this is the specific excess power, right? So this diagram basically tells that how much airplane can still maneuver. And then this is a PS equal to 0 contour for 2 different airplanes. So this contour belongs to airplane B. Okay, and then this contour belongs to airplane A. So 2 different airplanes. You can compare specific excess power plot. Okay. So this plot actually tells quite a bit of information for you. Both aircraft have a maximum thrust condition, 50% internal fuel, 2 times IR missiles, and n equal to 1. So this is a rebel flight, not maneuvering, but maneuver weight, sort of. So combat ready type of configuration, straight rebel flight. And obviously, those 2 airplanes are designed for different regime of the flight. In other words, airplane B is sort of higher altitude and lower speed range type of airplane. So this flight envelope covers the lower speed and then higher altitude, sort of, relatively speaking. And then this airplane A is higher speed, but the altitude is about the same, but some of the altitudes airplane B have advantage or sometimes exclusive. Airplane A cannot maneuver around here. So especially low speed and from low to high altitude, airplane B has advantage. And then airplane A at the high speed range, almost from low to high altitude, it's got exclusive advantage against the airplane B. So you can sort of tell those things by comparing, okay? This is aircraft PS comparison, okay? So you are seeing airplane A and B. Aircraft A would attempt to bring the dogfight, if they choose to do so, to a lower altitude and higher speed. That's airplane A. Yeah, sure. This is high-speed airplane. Obviously, the maximum speed is also different. Maximum speed of airplane B is about 1,100 or a little bit less. Airplane B goes up to 1,200. Slightly lower altitude, however, something like that. So aircraft B is designed for low speed and then higher altitude, looks like, okay? Now, obviously, you need to compare those 2 airplanes with a lot more other data also, load factors, wing loading, engine size, other things, okay? So that is the PS comparison. So today we want to talk about the maneuverability diagram. So this is the diagram we want to take a look at. So this is an interesting plot. It's a composite plot. Lots of information is plotted in single figure. So you have to be very careful by reading it. This is based on the single configuration. This is a fixed configuration. This is a 50% internal fuel, 2 AIM-9 missiles, maximum thrust. Weight is 21,737 pounds specific, and then altitude is 15,000 feet. So over this configuration, this is the load factor. Load factor 987,654. This is 3 and 2. So load factor plot is 2 to 9, positive load factor. And then plotted against, this is the turning radius. Turning radius is also a contour, straight line. This is the turning radius, 1,000 feet, 2,000, 3,000, 5,000. Now, one thing which is missing is 4,000 feet. 3,000 to 5,000, it's kind of skipped. So I wish I would add one more line here. So 4,000 is in between 3 and 5. So I'm going to add another straight line, something like that. This is 4,000. Before we move on, okay? For some reason, 4,000 feet line is missing, okay? All right. And then other things. This is a PS equal to 0 contour. Let me just trace out with different colors. So this is a PS equal to 0 contour line. It's plotted like this. That corresponds to one of those things, okay? And also, this one, okay? This is the aerodynamic stall limit line from the BN diagram. Okay. So if you go back to BN diagram, this is the aerodynamic stall limit line, which is this line. This line. Okay? It actually corresponds to this line is plotted. Okay?
Wait,
Yeah.
so for those two lines, is anything on the line or is it anything above or below?
This is
No, I'm talking about like the graph from before.
the other graph, okay. So the other graph is, so this is the aerodynamic stall limit. That means, okay, so everything above is stalled.
So it can't do any of those turns.
That's right.
No.
That's right.
Wait, and if PS is equal to 0, that means anything above that isn't also technically possible, is that correct?
That's right. So it's actually instantaneous. PS equal to 0 is going to make you sustainable turn.
Anything
Sustainable.
above it is unsustainable.
Anything above is non-sustainable, but you can still instantaneously perform that. So this actually tells you instantaneous performance too. It doesn't sustain. Okay.
So it could pull it for like a second and then lose it.
That's right.
Okay.
That's right. Okay. Instantaneous. So right here, so the maximum load factor 9, and then this aerodynamic stall limit crosses over here. This point is a corner velocity. So this is a B star. Okay. So this is a combination of BN diagram, sort of, BN diagram plus turn radius over product on top of it. So this is the energy maneuverability diagram. An important thing is because of the PS equal to 0 contour is also plotted, PS equal to 0 inside of this contour is sustainable because you still have excess power, but outside of it, you cannot sustain it. You can only instantaneously turn that radius, okay? But you cannot maintain that, okay? So anyways, so this is called maneuverability diagram, energy maneuverability diagram, okay? So one of the important thing about that is, yeah, I guess lots of things already discussed here. So this is the combination of excess power and the BN diagram. So those two are combined. At least PS equal to 0 contour is given. So PS equal to 0 contour is over product with the BN diagram. Okay. So this is basically a plot. The turn rate and the turn radius can also be read from it. Okay. So both information, turn rate and turn radius can be read off. That's why this is called maneuver diagram. Okay. And so this is basically plotted for fixed aircraft weight, configuration, altitude. Yes. And okay. All right. So this is actually kind of interestingly confusing. Okay. So you have to think a little bit about what it means. Okay. Absolute minimum turn radius. absolute minimum turn radius is not achieved at corner velocity, but at a lower speed if, okay, if corner velocity is beyond Mach number critical. Oftentimes, this is the case. Corner velocity oftentimes is above critical Mach number. If so, corner velocity is not going to give you minimum turn radius. Okay, it could give you maximum turn rate, but turn radius is kind of overshoot because you're flying really fast speed. But typically, the corner velocity is the choice for turning, usually. So let's be careful about that. If the corner velocity is beyond the critical Mach number, you can only get maximum turn rate, but not the minimum turn radius. Minimum turn radius, in order to achieve that, you have to fly lower speed than corner velocity. If the corner velocity is beyond critical Mach number. This is actually happening for high-speed airplanes. Especially if you design for your high-speed airplane, corner velocity is much, much higher than critical Mach number. In such a case, you can actually maximize the turn rate, but you cannot minimize the turn radius. In order to minimize the turn radius, you have to fly slower. Does it make sense? Most of the airplane you design is a low-speed airplanes. If so, don't worry about this. If it's a low-speed airplane, corner velocity period, that actually both maximum turn rate and minimum turn radius, both. So in this case, for high-speed airplanes, you have to fly slower to minimize the turn radius. Okay? All right. So that's what I'm trying to say here. So for your design, I guess every single airplane that you're designing right now is probably corner velocity is the minimum turn radius, maximum turn rate anyway. So don't worry too much about it. But some of the high-speed airplanes, this actually happens. Okay. So this is the example C43, okay? There are 3 questions for this example program. Okay, let's just take a look. What are the maximum instantaneous turn rate, minimum instantaneous turn radius, maximum sustained turn rate, and minimum sustained turn radius at h equal to 15,000 foot? This is the plot for h equals 15,000 foot for the aircraft whose maneuverability diagram is given here. Okay. Wait, this is a Mustang, isn't it? Flip float. Sorry about that. I show you notes. I'm looking at Mustang notes. It was opposite. Sorry. Too bad. Okay, so I'm going to bring it up the figure, on the figure. Okay, so this is on the figure. Because I really want to zoom in to this figure, okay? All right. So first question is, what is the maximum instantaneous turn rate, okay? So number 1, maximum instantaneous. So you're talking about, this is, what's the condition for that? This is a corner velocity. Now, question is this sustainable too? It depends on your PS diagram, of course, yeah? Corner velocity, V star. So you're going to pick up the corner velocity. Corner velocity is, okay, if you really zoom in, corner velocity is the crossing point between aerodynamic stall limit reaches to the maximum load factor limit right here. So this is the corner velocity. So you can read off the Mach number corresponding to this. This is the corner velocity Mach number. And then you can basically read off this value about here. That's the rate of turn. So this is the instantaneous maximum rate of turn because your airplane is flying at the corner velocity. Okay? So let's just go back here. So this really is, this is going to give you the read off of Mach number. What's the Mach number, by the way? Anybody? 1.15 based on the textbook.
Oh, pretty.
That's pretty good. And then rate is about 15 degrees per second, by read off. Okay. So this is actually corresponding to corner velocity. Okay. Question number 2, minimum instantaneous turn radius. Okay. So this is like, it depends on stall characteristics of your airplane. In other words, you want to make a very, very tight turn without airplane being stalled. Okay. So this is a crossing point between aerodynamic limit line crosses the lowest valued constant turn radius line. This is kind of tough. The reason is, I added one line. Where is, oh, okay, sorry. Let's just go back here. So what I'm talking about is, okay, so this is the aerodynamic stall limit line. Along this line, your airplane actually stalls or not stalled, it's just a borderline, okay? Anything above, your airplane stalls out. So by maintaining this line, what is the minimum turn radius? Well, obviously, turn radius 3,000 feet is impossible. So it's going to be bigger than that. Now, so is that 5,000 feet? I don't know. Suppose I can only imagine 4,000 feet turn radius, but it's not drawn here. But it looks like it crosses. So let's just come up with the imaginary 4,000 feet turn radius. I don't know why it's missing. So in between 3 and 5, right? Looks like. So if you draw a line in between, looks like this is the line. This is, suppose if I use the straight edge or something, so this is 4,000 feet turn radius. It looks like, okay, wait a second, it could probably possibly go to 4,000 feet if you maintain, I don't know, around here maybe. So I can possibly turn 4,000 feet with barely not stalling airplane. That's what it is. So what is the Mach number here for that? And what is the turn rate for that? Anybody? Mach
5.5.
Textbook says Mach 0.6 and 4,000 feet. Yeah, because it's 4,000 feet. Barely touching 4,000 feet at the Mach 0.6. In other words, if you maintain 0.6 Mach number, this is the load factor 3, or a little bit above load factor 3. 3G turn with Mach number 0.6, you can turn 4,000 feet. This is probably most likely minimum turn radius. That's what the textbook says. Do you agree? Okay. So you can read off Mach number approximately 0.6. Minimum turning radius 4,000 feet. Okay. Now, if this is an exam problem, I will probably add 4,000 feet line by myself for the figure, so that make it more clear. This is not so clear. This is probably the second nature of Air Force Academy people. Make things not so clear. I don't like it, but anyways. So third question is, okay, so what is that question? What is the maximum sustained turn rate? By the way, one important added comments here, okay? So this is minimum instantaneous. Is it instantaneous? Can you sustain this?
Yeah.
Yeah.
Oh, yeah.
Oh, yeah. This is under the contour of PS equal to 0 line. So this is actually sustainable. Okay? So this is actually minimum sustainable turn radius also. So in other words, you have a pretty good excess engine power for this case. Okay? So question number 3. What is the maximum sustained turn rate? So now you're talking about max sustainable turn rate. This is on contrary to the question 1. Question 1 was a maximum instantaneous turn rate. Now you're talking about, okay, so what is the sustainable turn rate maximum? Okay, so this actually comes into play at this is PS equal to 0 line intersects with aerodynamic limit line. So this is the condition. In order to sustain the maximum sustainable turn rate, you have to consider both. In other words, PS equal to 0 line contour and the aerodynamic limit must cross together. That's going to be a maximum rate. So if you go back to the figure here, so this is aerodynamic stall limit crosses over with PS equal to 0 line contour here. Let me just trace out. So this is a PS equal to 0 contour. So those two cross over here, right here. So this is the maximum sustainable turn rate. Now obviously you can bump up to this turn rate. This is the maximum, but you cannot sustain it because it's above PS equal to 0, right? It's a corner velocity though, okay? So you are going to read off this value. So this is maximum sustainable turn rate. Okay, what's the value?
12.
Yeah, 12, okay. Textbook says 11.5. How about Mach number?
That's it right for the first time.
How about Mach number?
This text.
0.78, that's what textbook says.
Wow, okay.
Wow.
But I'll give you both correct answers. You know, you don't have to be super accurate. So this is going to be what the textbook says, Mach number 0.78. If you say 0.8, it's correct. Turn rate is 11.5 degrees per second. If you say 12, that's okay. I mean, it's impossible to read off accurate value like this. Okay, Any question here? So mainly your read off is turn radius and also turn rate, okay? And then constrained by aerodynamic limit line. In other words, you're going to have a stall if you go beyond it. And also PS equal to 0 line is essentially that's how much your excess power no more available. That means you cannot maneuver anymore beyond that contour. PS equal to 0 line. Okay? Any question here? Like I said, this is very easy target for the exam because exam problem, I can basically cut and paste this figure and then, hey, find out what is the minimum sustainable turn rate over, I don't know, load factor 7 or something like that. I can create any question I want. You can read off the value from here. Okay, so this is quite interestingly important figure here, and also important figure here is a PS diagram. So if I give you this kind of PS diagram, I can create a bunch of questions so you can read off the values. Okay. All right. So let's just take a look at the constraint analysis. This is going to be your quiz file. The last quiz of the semester is going to come up from constraint analysis. So why do we need to do constraint analysis? In other words, this is going to be a plot of two unique parameter of airplane. One is this, one is that. Have you ever heard of this? This is a takeoff weight divided by area S. This is something called wing loading. Wing loading.
The wind?
Wind, not the wind. Wing. I have a tendency of that mistake. Wing loading. Okay. So high wing loading airplane sitting right next to the bookstore. That's a very high wing loading airplane. Okay.
Great.
Yep.
For the exam from home, did we get 2 minimum sustained turn radius?
Do we get?
That's just this.
No.
Oh,
Yeah.
minimum sustained, the other.
Yeah, that's
Yeah,
right.
minimum sustained. Oh.
I might keep saying
Well,
maximum.
one is sustainable, the other one is the minimum.
Wait a minute.
Or maximum.
No. It's all good.
Yeah, it's all good, the answer there, in the orange.
Oh, okay.
Yeah, that's right. So this is sustainable. Sustainable at the same time instantaneous, both, because it's under the PS equal to 0 control.
It's not
Yeah, yeah, that's right. And third question is,
Maximum.
Maximum tab, I'm right.
yeah, that's right. So maximum instantaneous turn rate is this. Minimum instantaneous turn radius is this. And maximum sustainable turn rate is this. Yeah. Yeah, okay. And did I answer minimum sustained turn radius? Ah, that's this one, right?
Yeah, that's
Okay. Sorry, I'm slow. Slow to understand. Okay. I'm getting old. I cannot reflect. Yeah, I need some time to think about it. Anyways. Okay, now, how about this then? This is thrust to weight ratio. Huh. So those two are actually quite important design parameters because this actually determines almost like your size of airplane, right? In other words, thrust to weight ratio is how big your airplane's power plant should be. How, what kind of engine should I choose? How many do I need? That's the thrust to weight ratio. Of course, it depends on your weight of your airplane. So suppose if you come up with like a monster airplane, just like you guys are designing. Right, so you need, I ended up needing like a 10 jet engines, like
Yes.
and then wing loading is like, okay, how big your wing is. Can I just support this heavy tanker airplane with this kind of wing? No. So This is going to actually determine your airplane's characteristic sizing, initial sizing almost. Huge impact on your initial sizing. So you really want to have solution space. That means, hey, this is the possible choice of combination of a thrust to weight ratio and wing loading based on the constraints. In other words, constraints is, okay, how much landing and then takeoff distance does this airplane need to satisfy? That's also one constraint. The other constraint is, what is the other constraint? Like a turning radius, takeoff and landing, what else? Turning. Wait a minute, let me just look ahead. Yeah, turning constraints. So we need to have this much subsonic and supersonic combat turn radius we need to maintain. And also, this airplane need to take off with this much distance, need to land this much distance. Those are the constraints, okay? So those are the requirements it's actually coming from when you start designing your airplane. So your customer keeps saying, we want to have a very high-speed supersonic airplane, but capable to turn really small radius and then take off landing with this much. And then you go like, what are you talking about? You cannot design like that. There's no solution space for that airplane. You can only imagine. So you have to start with this constraint analysis to begin with. Realistically speaking, what kind of range of a combination thrust to weight ratio wing loading we can have? That's called solution space. Okay. So constraint analysis comes with master equation to begin with. So master equation coming straight from, this is the excess power equation. This is the specific excess power equation, which is velocity times thrust minus drag. Obviously, thrust information comes from your choice of power plant. Drag is how beautiful your airplane is designed aerodynamically using X prior 5. That's drag. Yeah, that's right. You spend all of those times coming up with this drag, minimized. Okay? And then how heavy your airplane is. Like one of the insane requirements of SAE is, okay, you have to bring this much hunk of metal. And then you go like, what are you talking about? With this much wingspan? Let's go for biplane. That's why you go for extreme choice. Okay. So again, so this equation is going to be change the form and come up with a master equation. Master equation is, okay, so this is a function of, this is the thrust to weight ratio. This is a function of wing loading. So you can plot thrust to weight ratio to wing loading as a function. So this function depends on those parameters. Parameters include alpha, beta, W, takeoff, wing area, S, Q, and N. N is the load factor. Okay. So this is the master equation of constraint analysis. Then you can actually plot the constraint diagram. Okay. So let me just go ahead, take a look at the constraint. So what kind of constraint are you going to consider? One is a takeoff and landing. So takeoff and landing equation we covered in unit C3. It's going to be expressed in terms of thrust to weight ratio and the wing loading. So this is the alternative equation to the takeoff constraint. So takeoff constraint, in order to satisfy takeoff constraint of like, okay, we need a 2,000 feet takeoff distance, you're going to come up with this plot. This is the thrust to weight ratio as a function of wing loading to satisfy that 2,000 feet takeoff distance. Okay. Landing constraints also very similar to it. So this is a constraint equation for airplane landing. In order to have this airplane land in 2,000 feet runway, what is the relationship between, this is wing loading also. Oh, this is only wing loading. That means with a heavy airplane just like you guys with this much wing, you can never satisfy this. You need to have certain airplane area, wing area, you need to satisfy. Or make your airplane much lighter. You do something, otherwise we can never satisfy this constraint. So you're going to come up with what is required to satisfy this constraint. Okay? So let's just take a quick look at example C44. This is the constraint analysis example. Okay. There are a few parameters you can only estimate, so let's just be careful about that. I'm going to go slowly here, okay? So this is a constraint analysis example. Based off of this example, you're going to work on the quiz 5. Quiz 5 is a constraint analysis quiz, okay? What is the airplane I want you to analyze as a constraint analysis? That is one of those stealth airplanes, F-22 prototype 1. I'm going to give you all sorts of constraint requirements you're going to analyze and find out the design space. That's the quiz 5. That's so cool. Yeah, that's going to be a last quiz of the semester.
Give us more than a day to do it.
I haven't made up my mind yet. Do you have a request? Do you want to make it do like a tomorrow morning?
No,
Something?
can we give like a couple days to do it?
Next week, right?
Yeah.
Yeah, okay. Yeah, it's going to take some time, this quiz will be.
Yeah, that's what I was asking.
And then I'm thinking probably, how many points did I give you for like the previous four quizzes? 20 points?
They were usually 1 out of 10. But
Yeah.
Out of 10, right?
Yeah. then you
This
double-
quiz, I don't know, I can make it like, I don't know, 50 points or something.
And then you get double that.
Yeah, you can basically recover all of those lost points in the previous quizzes. If you do it right. If you screw up lots of points. Okay, anyway. So let's just take a look at,
Yikes.
yeah. I think it's easier this time. You can do a better job. So constraint analysis example here, consider the multi-role fighter design requirements from table 1-2. Let's just go back in table 1-2. Table 1-2 is, where? Table 1-2 is, this is table 1-2. Okay? Remember that? So this is the constraint, in other words. So requirements comes in. Combat mission radius 400 miles, weapons payload, this is the maneuver weight. Takeoff and landing distance 2,000 feet period. And then you have also instantaneous turn rate and specific excess power 4G at Mach number 1.2, 20,000 feet mean sea level. So this is like a 20,000 feet altitude. When you're flying Mach number 1.2, you have to have a capability of 4G level turn. You have to have that much specific excess power. And then also, this is a sustained load factor of 9G at Mach number 0.9, 5,000 feet. So we are going to tentatively call those, okay? This is a supersonic turn. This is subsonic turn, okay? Those are actually constraints. So this is a supersonic turn constraint. This is a subsonic turn constraint. Also, the other two constraints you can pick it up from here is, of course, takeoff and landing. Those are also constraints. Okay. So in this practice exercise, we are going to basically come up with 1, 2, 3, 4 different constraints. You are going to plot it over thrust to weight ratio and then wing loading plot. Determine the design space out of those 4 constraints, okay? So let's just take a look at notes C4. Here we go. Okay, so table 1.2, as you saw, specifies the following performance requirements. So this is the combat turn, this is the subsonic. Subsonic combat turn radius, Mach 0.9. Okay, so this is combat turn, maximum afterburner. You're going to turn on the afterburner and then try to do 9G sustained 5,000 feet, Mach number 0.9 subsonic turn. This is a supersonic turn. You're going to, of course, again, maximum afterburner, 4G sustained at the 20,000 feet, Mach number 1.2. This is supersonic turn. Okay. So those are the 1 and 2 constraints already. Now 3 and 4 constraint, takeoff and braking distance, STO, equal to SL is 2,000 feet. So this is takeoff and landing constraints. So 1, 2, 3, 4 constraints. Okay. Yeah, go ahead.
When it says maximum afterburn, is that for the Mach number? Is it better than or that Mach number?
Well, maximum afterburner 9G turn. Wait. Yeah, this is subsonic.
No, I'm saying that if it's maximum thrust,
Mm.
shouldn't your maximum thrust be able to exceed point past Mach 1.9? So is it what Mach 1.9 and better?
But it takes energy to do that turn, so you're sustaining that Mach number and that.
Yeah.
In other words, this is not rebel flight. So this is a maneuvering. So 9G turn is a really sharp turn in subsonic speed. So maximum afterburner, you try to really do a tight turn in subsonic speed.
Okay.
Yeah. So this one is a supersonic and high altitude. So you are not really picky about the load factor because this is 4G turn. That's the only thing you require. But it's a supersonic speed and higher altitude.
Okay.
Yeah. So this is actually going to determine the size of your power plant, at the same time how heavy and strong your airplane should be, kind of thing too, right? So those are the 4 constraints. Okay. Now before you move on, I guess the first question is, can we really make that kind of stuff? Isn't this like absolutely insane that no one can satisfy this constraint? Do we have a design space? That's the one thing we want to find out. Okay. So that's why the purpose of this constraint diagram is we want to find out the design space. So first of all, we are going to calculate the subsonic combat turn. Like I said, this is 5,000 feet altitude, Mach number 0.9. Okay, so 5,000 feet altitude, speed of sound density is given. So airspeed is 987.2 feet per second. Dynamic pressure is 997.9 psf. Important thing is this is estimate, okay? Since this is a maximum afterburner, alpha is a thrust over thrust sea level. Thrust sea level, military power, to this situation, maximum afterburner thrust is estimated 1.4 times bigger. This kind of information you cannot easily get. Either I have to give it to you or you can actually do not a really good estimated guess, okay? So this is 1.4 times because this is a maximum afterburner. Okay, max AB. So thrust to sea level, installed military thrust is 1.4. This is like a maximum power you can squeeze out from your airplane. Weight fraction, this is also, again, estimated by you. Over this maneuver, you are going to maneuver with the maneuver weight, which is the 2 AIM-9, no, AMRAAM, 2 AMRAAM, and then 2 Sidewinder, full ammo, half fuel. This is maneuver weight. So this is 0.8 times takeoff weight. So this is again estimated by you. Okay. So this is a W maneuver. Weight of maneuver. So this is actually resident takeoff weight. Okay. Let's assume that way. This is a load factor 9G, sustained turn. Aerodynamic properties, we actually computed for F-16. Remember that?
Yep.
Unit B3, that's right. So this is something you did by hand also. So this is CDO, K1, and K2. Okay. So we are going to pick up the master equation for constraint analysis. You're going to compute TSL over WTO. This is the thrust to weight ratio. And then you are going to actually ignore the external storage induced CDX. We are going to actually, sorry, I skipped it, but parasite drag is going to be split into 2. I think I skipped it. Yeah, here we go. So for convenience, we are going to break the parasite drag coefficient into 2 parts. So this is zero lift drag of a clean aircraft. The CDX is external storage. In other words, you're going to put your external fuel under the wing, rocket pylons and stuff like that. If you add those things, you're going to add this. external CDO. So this is the parasite because you're going to add more ammunition under the wing kind of thing. Okay? CDO is a clean configuration parasite CDO 050 drag coefficient. So I skipped it, sorry about that. So that's actually completely ignored. Zero. Yeah, for this turn maneuver, because this is the maximum afterburner with the maneuver weight trying to do 9G turn. So hopefully you are not having like under the wing missiles when you do that. Actually, simplify it. Okay. If you're picky, you can include this, of course. So this equation gives you the value of table 2, 5.2. So you're going to compute the value of thrust to weight ratio as a function of wing loading and then create the value of table 5.2. That's what this thing is. So this is the F-16 subsonic combat turn constraint. Okay? So you can plot this data, okay, into XY plot, okay, which is going to be this plot. This is a plot you're talking about, subsonic turn constraint, okay. Next is a supersonic turn. Let's just do the similar thing. So supersonic combat turn is a given information altitude 20,000 feet high altitude, and then speed of sound is different, density is different. This is supersonic, Mach number 1.2. This is going to give you different dynamic pressure. Now this is the thrust reps ratio once again. This is a full afterburner on, however, it's higher altitude. So thrust reps ratio drops from 1.4 to 0.98 simply because this is higher altitude. This is maximum afterburner. Once again, this is estimated by you. Okay. So this is the lower altitude maximum afterburner. Thrust to sea level thrust ratio is 1.4. This is slightly lower. Okay. Even though you turn on the full afterburner because it's higher altitude, you can get about the same thrust as if you are sea level without afterburner on. That's what it is. This is the same weight fraction, 0.8. Again, this is the maneuver weight. Half fuel, half ammo kind of thing. Okay. And then aerodynamic properties are different. Okay. Now it's different. Again, this is computed from unit B3. High speed CDO, which is different from low speed CDO, obviously. Okay. So using all of those information, you can come up with the master equation of thrust to weight ratio to the wing loading. Now you are going to compute this and then come up with the value listed here, table 5.3. So this is the computed results of supersonic combat turn constraint. You can plot another line, okay? If you plot this, it's going to be this line, okay? So this line is a constraint of supersonic turn constraint. So now you plotted two things. This is subsonic turn constraint. This is supersonic turn constraint. Anything below of those two curves are gone. You cannot satisfy such a thing. You have to be above both of those curved plots, okay? Next is landing and takeoff, okay? Takeoff is, of course, you're going to come up with a takeoff constraint equation here, okay? Altitude is 0, of course. CO max for takeoff come into play. Thrust to reps ratio, this is 1.105. This is because when you take off, you can possibly turn on afterburner. So this is with afterburner, you can bump it up, the thrust from thrust to sea level 1.105 with afterburner on. So this is again estimated. AV on, okay? If you take off without afterburner, it's going to be 1, obviously, okay? This is a weight fraction, of course, takeoff weight. Weight is a takeoff weight, yes, right, okay. And then loading friction coefficient, this is average for the paved runway. This is a CDO 0.059. Typical value is 0.05. Takeoff configuration, landing gear down, plus flap and flap it on full down. This is actually informed in unit B3. This is F16 information. Okay. With all of those values plugged in, this is another plot, table 5.4. This is the data set you compute for takeoff constraint. Okay. Now you can plot this value. This is the takeoff constraint. Okay. Takeoff constraint is kind of linear line, obviously. Anything above, you're satisfied. Anything below, you're not. Landing is a straight line up. Okay. Because this is only this wing loading. In order to have a 2,000 feet landing, you need to have this much wing loading. Okay, so this is the vertical line, this is the landing constraint. So if after everything is plotted, this is the potential solution space. You're going to choose any location within this solution space, but you want to pick usually something close to here, just the minimum value, minimum for both sort of. Okay, so you're going to do the same thing for quiz 5. This is constraint analysis. I guess you guys probably did it in senior design. Is that true? Did you do constraint analysis in senior design project at the very beginning, at the conceptual stage?
We're not seniors.
You're not seniors, right?
No, we're not seniors.
Really?
You didn't do that.
I thought we had seniors. Anyways, so you're gonna probably do this, okay, at the very beginning of conceptual stage. In other words, this is going to eliminate some of the configurations you come up with. This may possibly eliminate your teams like Canada configuration. I don't know. I hope not. If so, you have to reiterate.
Well,
Then you go, oh, you realize, oh my goodness, Canada airplane was a bad idea. This could be. Okay? This is the typical value for lots of variety of airplanes. So now, let me inform you. I'm going to give you quiz 5, which is this airplane. Yeah, this airplane. You're going to do quiz 5. So make sure you come up with a reasonable value of actual design point. This is the design point YF22. You're going to come up with that based off of the constraint analysis you're going to perform. Quiz 5. Okay. All right, so do you have any question here? That's it for Unit C4. Have a great weekend, and then we're going to see you back on next week, and then I will give you an announcement today about Quiz 5, okay? And also probably phase 3 of the project, too. Okay? Any question? Any question online, people? Have a great weekend.
You didn't come to what? Yeah, that's not.
We also.